Good morning, everybody. I want to, this way, give you a status update of the OPC UA working group and the activities there. I have another presentation later where I talk about the so-called companion specification. That's how where we work with other organizations together. But this is mainly about the core OPC UA, OPC Unified Architecture activities and working group. Should that work? Okay, helps. On. Okay, so just to give you a little bit history with OPC, before OPC. So devices talk like different languages, different grammar, even different character sets. And the first solution of OPC Classic was to, let's put a PC there and install translation software. So that allowed us to exchange simple information, but it's the, let's say, the old way of doing things. With OPC UA, the idea is that devices, applications talk the same language, but not only the same language, they also can have like security features like identify themselves, protect the communication, and to have like some basic grammar and understanding of communication. So to really have like not only a bits and bytes exchange is to really understand each other on a semantic level, and the important step for that are the OPC UA information models, where domain experts or groups for certain areas and use cases define even special meaning of things and how to interact between applications and devices on a much higher level than bits and bytes. So to have really a semantic understanding and semantic interoperability, not only a protocol interoperability to provide also semantic interoperability. That's the idea of OPC UA and what we do in these companion working groups. So first of all, I want to give you the status of the OPC UA specifications, so what is released, what is available today, but also outlook to new tasks of the OPC UA working group, activities we're working on at the moment. And for OPC UA, like we had first versions of the specification 2007, but the first public release was 2009 with like all the basic functionality and that was also like the starting point where you can get OPC UA products like what Stefan mentioned. Was like Beckhoff had OPC UA server on the PLC, Siemens had one on the PC with the Semantic Net OPC UA server. Iconics was also one of the first providers of OPC UA products. And very close to that, we also provided certification tools, which is very important to verify the quality of products, if to have a way to certify them, to provide test tools. And based on this, like if you do a standard, it's a set of paper, and there are a lot of different implementations of the standard. So it's very important to have the loop of verification of implementations, and anything that comes out of the verification where you have like a different understanding between people that write test tools and people that provide products, that has to go back to the specification. So it's a cycle, a maintenance cycle, to add clarifications to the specification, to remove any ambiguities. And so this was like an important part of all the releases we have now is these compliance clarifications. But we added also in 2012 a few new features like 2 new protocol versions, and historical access was released at this time. And now in July of this year we released version 1.3 of the OPC UA specification, and we added there a network-wide discovery as new feature, a central certificate management. I will talk about these features a little on 2 or 3 slides. And we added also features like new variations of structure data types, like support for unions and optional fields in structures and bit mask data types. So that was done in July this year. One change on the protocols, like in the first protocol bindings we released were the UA binary, UA secure conversation, UA TCP. So that's the mandatory binary optimized protocol for OPC UA. But in the first version we had also a web service binding. In version 1.02 we added HTTPS, so transport layer security versions, especially for web browser-based applications, because they have not direct access to crypto libraries, which is required for this message-based security we normally prefer. And in 103 we deprecated this variation because of not really any adoption in the market, especially this whole stack of standards, this WA secure conversation. The expectation was that this is implemented by all standard web service stacks, that did not happen. So we have still, if you talk about web service, you have still this combination of SOAP 1.2 and XML encoding with HTTPS, which is the only security that is really available in all of the SOAP stacks. So that's why we deprecated that version. For the new features, the most important one was the network-wide discovery. So that's a new OPC UA Part 12 discovery, and it defines different discovery concepts, but also like a central certificate management concept. And one is an ad hoc discovery using the MDNS standard, which is a multicast extension for DNS. And the idea is that OPC UA applications, OPC UA servers announce themselves in the network using MDNS, so it's a service discovery, but MDNS also supports name resolution if you don't have a DNS server installed. So it's a decentralized approach for name resolution and service discovery that is like a feature that is a standard feature in Linux-based installations, and Apple Bonjour is also using MDNS, and so we use that. And to enable the easy integration with existing OPC UA applications, OPC UA servers, they register with a so-called LDS, a local discovery service, that provides a list of available OPC UA servers on a network node. And since this registration is already done, just with the update of this LDS to a LDSME, so that's local discovery service with multicast extension, there is no change necessary on the servers. It's just the update of the component provided, shared component provided by the OPC Foundation, and this component is then doing the announcement of the servers in the network using MDNS. And the only new thing for OPC applications is that this LDSME also provides a cache of available servers in the network. So there's one new service that can be called by client, and it's called Find Servers on Networks. So it gives you a list of all servers that are registered, or OPC UA services registered or announced through this MDNS extension. So that works nice in a local network without central infrastructure, but it's probably limited to subnet. And we have a second concept called global discovery service, and that's a central server in a system that allows that has a list of registered OPC UA servers, and so it allows a network-wide discovery of servers, and especially also a discovery with security. So if you, that's one of the problems with discovery. It's a chicken and egg problem. If you don't know the security settings of a server, you cannot use security to get the information. So therefore, the local discovery and the ad hoc discovery through MDNS is without security. So if you need a secured version of discovery, this GDS concept also gives you a secured version, because the GDS is a full OPC UA server with full security features. So you have then a way to also secure the discovery process in your environment. But that's one feature, but even the more important feature is a centralized certificate management, because the OPC UA security depends on distribution and management of PKI, of public-private key infrastructure, and public and private keys certificates. So everything you know from web browser application for HTTPS is also like the base technology for OPC UA. So the key distribution and the management of keys is a key feature for managing OPC UA security. And so this global discovery service provides a wrapper, a OPC UA wrapper around a so-called CA, certificate authority. So certificate authority is a concept to manage certificates in a central place and to sign certificates that are provided for applications. And by trusting a CA, you automatically trust all applications that have signed certificates from that CA. So it's a way to, so the CA, certificate authority, is a well-known concept in the IT world to manage certificates. And since OPC UA applications can talk OPC UA typically, we said, okay, how can we make this functionality available to OPC UA applications? So we just expose the CA functionality that is necessary for OPC UA through OPC UA interface. So this GDS has two interfaces. One is called directory type. It's used to register applications and to query for servers. So it's a discovery functionality. And then there's a certificate directory type that provides all the certificate management functionality. And so the initial setup of an OPC UA application normally requires some administrative rights. And so this administrative tool or application can then register the application with the GDS and can request certificates, or at least a signing request to the CA. So the CA then creates a signed public key for the application. So this is the initial setup of applications. But even more important is the update of trust lists and revocation lists, because the concept of a CA is like a blacklist where you have you trust everybody who has certificates signed by that CA, and if an application is not longer allowed to talk to the other applications, this certificate is added to a blacklist for the CA called certificate revocation list. And this list needs to be updated frequently. So all OPC UA applications need to get updates of these lists frequently. And this is done also through this certificate directory type, where the OPC UA applications can request updates to that list. And this is called pull model, where, so if you have an OPC UA application that is a client or a server with client functionality embedded, these applications can pull these updates from the GDS whenever they start up or in a time sequence, like every day or every few hours. But there are also cases where applications just OPC UA server, so it cannot go to another server and ask for something, and therefore we have also so-called push model. So we have a standardized API defined for OPC UA servers called server configuration type that allows remote administration of the security settings and the certificates in the trust list. And that can be used by a GDS client that is part of a GDS setup to fetch updates from the GDS and then to push it down to the OPC UA server. But this allows, like this interface allows also remote configuration of any OPC UA server even without a GDS setup. So you can have just a standalone client and you can go to the servers and do security administration with this interface. So it's not only used together with the GDS environment, it can also be used as a standalone feature. So this was like the biggest extension to OPC UA 103. Since OPC UA is also IEC specification, I also want to give you a short update on the IEC status of OPC UA. So the OPC UA specifications were most of them already released as a IEC 62541 in the time frame 2010 to 2012 as a first edition, and there was a second edition released in March this year, which is mainly OPC UA 1.02. So a lot of just minor updates and few new features, but also 2 new specifications, Part 11 historical access and Part 13 aggregates was added. They are not included in the first edition. And we have the first companion specification that was added. So that's Part 100 devices, so that's device configuration. I will talk about that later in my companion specification talk. And we are also working on Part 12 discovery that was added in 103 as a new part for the IEC version. Okay, so the next part is what is currently the main tasks of the OPC UA working group. And Stefan said already, OPC UA is more than a protocol. And OPC UA has a lot of like infrastructure features, like provides security, it provides like definitely protocol interoperability, platform independence, but protocols are like something that can be extended and replaced over time. So protocols are just used to transport data from A to B. The key feature, especially long term, is the information modeling capabilities of OPC UA. And therefore we have like a OPC UA meta model where the rules for exposing an object-oriented model are defined. So all the basic rules, like for a programming language where you have all the language constructs defined, but nobody would use like a programming language just with the basic language constructs. You always, like if you use Java, you use always like database libraries, GUI libraries, other stuff that you don't reinvent every time you develop something. And that's what we have with these built-in information models. So it's like libraries for standard functionality. Like data access is like an analog item type that represents an analog measurement with a unit and a range property. Or the alarms and conditions model is a very rich model to expose or to handle alarm systems or alarm interaction. And so every time you have alarms to provide alarms as a server, as a system, or you want to consume alarms, you better follow the alarm condition model. It's the same like you would not reinvent a database library for Java, I assume. And that's the same idea for OPC UA. We come up with basic models that can be reused and can be implemented and also used for further modeling. Then we have these companion information models. They really define semantics for special domains, special use cases, special devices, and they use like the built-in information models, they extend them. Sometimes they also introduce new base constructs, and often this part here is then slowly moved into this built-in models. So a lot of companion information models already influence the built-in information models and requested extensions. And so the idea is OPC UA defines how information is exposed and transported, and domain experts define what kind of information with what semantic is exchanged. Then we have, like always, capability to have vendor-specific extensions, and that's very important. I learned that from other standards where they have just a fixed object model, and as soon as you have any vendor extension, there's no interoperability at all. But you always have vendor extensions because that's the market. you can agree on a model like for auto ID device or for an injection molding machine, but every vendor of such a device or machine has additional features that he wants to expose to the same interface. And so that's no problem with OPC UA, because everything from object-oriented programming you can derive from the standard types, and you can extend them. There are a lot of features in OPC UA to make that information also visible then to OPC UA clients. But all the communication today is a client-server model. We have predefined services, so that's a client-friendly, well-defined API for clients to access information from a server, like a browse for available nodes, objects, variables, read and write data, call methods, subscribe for data changes for events. So that's all predefined API. And it's an abstract definition of that API. So on the application layer, you just care about that like abstract API and not really about any of the protocol details. And so that's the part where we can add additional protocols, deprecate protocols, add new ones whenever necessary, without changing the application layer code. And without changing, so a new protocol has no influence to the information models, has no influence to the services. So that's very important, that you, like more or less you update your software stack to integrate new protocols. But especially in the IoT environment and cloud-based applications, we got more and more requirements to also support a publish-subscribe communication model. And that's what the OPC UA working group started end of last year, and now is working full-time on it since we have OPC 103 released. Now the full-time work is on this pub-sub model, and the idea is like similar to the client-server model. We define an abstract model for configuring publishers and subscribers, a model that is independent of the transport protocols, and then we have different protocols, different protocol options to start with, but they can be extended over time. So in the first step, we have a UA Secure Multicast, so that's UDP-based peer-to-peer, and AMQP for cloud connectivity. But we talked already in the break about other options, so that can be extended as additional protocols. And the beauty of the client-server model is that every client can request exactly the information he's interested in. But if you have a lot of clients that are interested in exactly the same information, the downside is there is a lot of overhead in the server side for managing a subscription for every single client. And if a lot of these subscriptions subscribe for the same data, there's a lot of duplicated work to do inside the server and on the network. And so the idea of the pub-sub model is, in this case, in the client-server model, the client exactly requests what kind of subscriptions and what kind of data is monitored in the subscriptions. In the pub-sub model, the publisher or the configuration of the publisher defines what is published. So it's something like it's a pre-configuration of the data that is published, of the information of the events. And the idea is like you have a data set where you configure like a list of variables you want to send, or events that you want to send, and then you define a message writer that writes it through a certain protocol binding. And then you have some kind of message-oriented middleware that deals with the distribution to the many subscribers. And like one option for the peer-to-peer communication is to use UDP Multicast as the middleware. So a publisher can send out a message to a multicast group, and all subscribers can receive the messages. And the key thing there is we also define a security model for that, because multicast is a challenge, a security challenge, and that's one of the main work items we work on, is to secure that communication too. And the idea is that, like for controller communication, you can have a pre-configured publisher in one controller. You can have a pre-configured subscriber in another controller. So you have a controller communication using UDP Multicast. But the configuration can be done by a regular OPC UA client. So you can use a configuration tool to set up the publisher and the subscriber, and then they can communicate with each other. So that's one use case, peer-to-peer communication, controller communication. And the second use case is cloud connectivity, enterprise service bus connectivity, using cloud relays. And the first protocol we're looking into is AMQP. So the publisher is an AMQP client that connects to a broker, to a message queue in the cloud, and sends, in this case, JSON encoded messages to the broker, and then the broker deals with the distribution of the messages. And like I said, there are maybe different protocols that are used in the cloud environment, and the basic model can be extended with additional protocols, but the configuration model will not change for that. And so the idea is that you have the information flow is that you have a normal address space, you select data out of the address space, you set up a data set, and there's a configuration object for a data set, and then you define message writers, so you can have, even for one data set, can be sent through UDP Multicast and through AMQP, so you can send the data set also through different protocols. But for a protocol, you have like a message encoding, message security, message transport, and they are also configured through objects in the publisher address space or in the subscriber address space. So the pub/sub extension, the working group, like I said, was started already last year. There is a draft specification available with having the information model for the pub/sub getting stable now, and we're working on the protocol and security details at the moment. And there are a few open issues we're working on. But the key thing is we also established 2 new working groups, sub-working groups of the OPC UA working group. And because there was such a strong interest in this extension that we said, okay, we need to manage these people and focus on more details. And one is a pub/sub prototyping working group, and we have at the moment 54 members there. It's more than in the core OPC UA working group, and that working group was started just in June this year. So we get new members every week at the moment. And this working group is mainly working on use cases and prototyping use cases and demonstrations to immediately verify whatever is defined in the specification. So there's a huge interest in putting this new feature directly into products and to verify if it works or not. So that will hopefully speed up the verification of the new features. And then we have a second working group called TSN Evaluation, and it is a working group that checks how OPC UA can extend it with real-time capabilities. And I will talk about TSN on the next slide, but TSN is an extension to standard Ethernet to make standard Ethernet real-time capable. And there's also like a huge interest, and there are different companies, so there's some overlap, but there are also a lot of network companies in like Cisco and that are interested in pushing that forward. And so this is for the controller real time. There's not the idea to have a new field bus defined. The focus is on controller communication, and there is a lot of use cases where you need also real time on the controller communication, and there is no solution on the market today. You can say, okay, there is Profinet, EtherCAT, PowerLink, whatever, but there's not one standard that's supported by all of the vendors. So there is no interoperability solution on the market today, and the goal is to close this gap for controller communication. And that's why people even thought about making that possible is with the UDP multicast we are very close to requirements, communication requirements for real-time communication. The only problem we have is standard Ethernet is not real-time capable. So that's the only problem then with having this UDP multicast communication or UDP communication. And this gap is filled by TSN time-sensitive network, and there are different sub-standards that will be extended. Some of them are already released, some of them are still in work. But I think the most important one is like a time synchronization and the guaranteed delivery of messages and prioritization of messages. But the important thing is this will be available in standard Ethernet hardware. And so nothing we want to care about. The main thing is we need to look at the requirements for configuration and setting up such a network and what is required as OPC UA site settings for that. So that's the main task of that working group. Okay, so to summarize that, OPC UA provides a secure cross-platform environment for communication, provides generic services, enables multi-vendor interoperability, but also semantic interoperability. So not only bits and bytes can be exchanged over a protocol, the idea is to have a semantic interoperability, which takes a little bit longer than protocol interoperability, but that's the goal. And that's, I think, is one of the key things to be an enabler for Industry 4.0 and industrial Internet of Things. Thank you.
Okay, do you have any questions for Matthias? Good, because we are at scale. So thank you, Matthias.